Artificial intelligence machine-to-play AI is a once-in-a-lifetime commercial and defense game changer. Hundreds of billions in public and private capital is being invested in AI and machine learning companies. The number of patents filed in 2021 is more than 30 times higher than in 2015, as companies and countries across the world have realized that AI and machine learning will be a major disruptor and potentially change the balance of military power. Until recently, the hype exceeded reality. Today, however, advances in AI in several important areas, see here, and here, equal and even surpass human capabilities. If you haven't paid attention, now's the time. AI and the Department of Defense has thought that AI is such a foundational set of technologies that they started a dedicated organization, the JIHE, to enable and implement artificial intelligence across the department. They provide the infrastructure, tools, and technical expertise for DoD users to successfully build and deploy their AI accelerated projects. Some specific defense-related AI applications are listed later in this document. We're in the middle of a revolution. Imagine it's 1950, and you're a visitor who traveled back in time from today. Your job is to explain the impact computers will have on business, defense, and society to people who are using manual calculators and slide rules. You succeed in convincing one company and a government to adopt computers and learn to code much faster than their competitors and adversaries. Cool. And they figure out how they could digitally enable their business, supply chain, customer interactions, it says. Think about the competitive edge they'd have by today in business or as a nation. They'd steamroll everyone. That's where we are today with artificial intelligence and machine learning. These technologies will transform businesses and government agencies. Today, hundreds of billions of dollars in capital have been invested in dollars of AI startups. The U.S. Department of Defense has created a dedicated organization to ensure its deployment. But what is it? And compared to the classic computing we've had for the last 75 years, AI has led to new types of applications, e.g. facial recognition, new types of algorithms, e.g. machine learning, new types of computer architectures, e.g. neural nets, new hardware, e.g. GPUs, new types of software developers, e.g. data scientists, all under the overarching theme of artificial intelligence. The sum of these feels like buzzword bingo, but they herald a sea change in what computers are capable of doing, how they do it, and what hardware and software is needed to do it. This brief will attempt to describe all of it. New words to define old things. One of the reasons the world of AML is confusing is that it's created its own language and vocabulary. It uses new words to define programming steps, job descriptions, development tools, etc. But once you understand how the new world maps onto the classic computing world, it starts to make sense. So first, a short list of some key definitions. AML, a shorthand for artificial intelligence, machine learning, artificial intelligence, the AA, a catch-all term used to describe intelligent machines which can solve problems, suggest decisions, and perform tasks that have traditionally required humans to do. AI is not a single thing, but a constellation of different technologies. Machine learning, ML, a subfield of artificial intelligence. Humans combine data with algorithms, see here for a list, to train a model using that data. This trained model can then make predications on new data. Is this picture a cat? Call a dog or a person, or decision-making processes like understanding text and images without being explicitly programmed to do so. Machine learning algorithms, computer programs that adjust themselves to perform better as they are exposed to more data. The learning part of machine learning means these programs change how they process data over time. In other words, a machine learning algorithm can adjust its own settings, given feedback on its previous performance in making predictions about a collection of data, images, text, etc. Deep learning neural nets, a subfield of machine learning. Neural networks make up the backbone of deep learning. The deep in deep learning refers to the depth of layers in a neural network. Neural nets are effective at a variety of tasks, e.g. image classification, speech recognition. A deep learning neural net algorithm is given massive volumes of data and a task to perform, such as classification. The resulting model is capable of solving complex tasks, such as recognizing objects within an image and translating speech in real time. In reality, The neural net is a logical concept that gets mapped onto a physical set of specialized processors. See here, a data science, a new field of computer science. Broadly, it encompasses data systems and processes aimed at maintaining data sets and deriving meaning out of them. In the context of AI, it's the practice of people who are doing machine learning. Data scientists responsible for extracting insights that help businesses make decisions. They explore and analyze data using machine learning platforms to create models about customers, processes, risks, or whatever they're trying to predict. What's different? Why is machine learning possible now? To understand why AI machine learning can do these things, let's compare them to computers before AI came on the scene. A warning, simplified examples below. Classic computers for the last 75 years, computers, we'll call these classic computers, have both shrunk to pocket size, iPhones, and grown to the size of warehouses, cloud data centers. Yet they all continued to operate essentially the same way. Classic computers programming. Classic computers are designed to do anything a human explicitly tells them to do. People as programmers write software code, programming to develop applications, thinking a priori about all the rules, logic, and knowledge that need to be built into an application so that it can deliver a specific result. These rules are explicitly coded into a program using a software language, Python, JavaScript. See how Rust, the classic computers, compiling the code is then compiled using software to translate the programmer's source code into a version that can be run on a target computer, browser, phone. For most of today's programs, the computer used to develop and compile the code does not have to be that much faster than the one that will run it. Classic computers running, executing programs, once a program is coded and compiled, it can be deployed and run, executed on a desktop computer, phone, in a browser window, a data center cluster. In special hardware, programs applications can be games, social media, office applications, missile guidance systems, Bitcoin mining, or even operating systems, e.g. Linux, Windows, iOS. These programs run on the same type of classic computer architectures they were programmed in. Classic computers, software updates, new features for programs written for classic computers. Software developers receive bug reports, monitor for security breaches, and send out regular software updates that fix bugs, increase performance, and at times add new features. Classic computers hardware, the CPUs, essential processing units, see that right, and run these classic computer applications all have the same basic design architecture. The CPUs are designed to handle a wide range of tasks quickly in a serial fashion. These CPUs range from Intel x86 chips and the ARM cores on Apple M1 SoC to the Z15 and IBM mainframes. Machine learning in contrast to programming on classic computing with fixed rules. Machine learning is just like it sounds. We can teach a computer to learn by example, by feeding it lots and lots of examples. If for images, a rule of thumb is that a machine learning algorithm needs at least 5,000 labeled examples of each category in order to produce an AI model with decent performance. Once it is trained, the computer runs on its own and can make predictions and/or complex decisions, just as traditional programming has 3 steps: first coding a program, next compiling it, and then running it. Machine learning also has 3 steps: training and teaching, pruning and inference, predicting by itself. Machine learning training, unlike programming classic computers with explicit rules. Training is the process of teaching a computer to perform a task, e.g. recognize faces, signals, understand text. Now you know why you're asked to click on images of traffic lights, go crosswalks, stop signs, and buzzes, or type the text of scanned image in reCAPTCHA. Humans provide massive volumes of training data. The more data, the better the model's performance, and select the appropriate algorithm to find the best optimized outcome. See the detailed machine learning pipeline later in this section for the gory details. By running an algorithm selected by a data scientist on a set of training data, the machine learning system generates the rules embedded in a trained model. The system learns from examples to training data rather than being explicitly programmed. See the types of machine learning section for more detail. This self-correction is pretty cool. An input to a neural net results in a guess about what that input is. The neural net then takes its guess and compares it to a ground truth about the data. effectively asking an expert, did I get this right? The difference between the network's guess and the ground truth is its error. The network measures that error and walks the error back over its model, adjusting weights to the extent that they contributed to the error. Just to make the point again, the algorithms combined with the training data, not external human-computer programmers, create the rules that the AI uses. The resulting model is capable of solving complex tasks, such as recognizing objects it's never seen before, translating text or speech, or controlling a drone swarm. And instead of building a model from scratch you can now buy for common machine learning tasks, pre-trained models from others and here. Much like chip designers buying IP cores, machine learning training, hardware training a machine learning model is a very computationally intensive task. AI hardware must be able to perform thousands of multiplications and additions in a mathematical process called matrix multiplication. It requires specialized chips to run fast. See the AI hardware section for details. Machine learning, simplification via pruning, quantization. Distillation, just like classic computer code, needs to be compiled and optimized before it is deployed on its target hardware. The machine learning models are simplified and modified, pruned, to use less computing power, energy, and memory before they're deployed to run on their hardware. Machine learning inference phase, once the system has been trained, it can be copied to other devices and run. And the computing hardware can now make inferences as predictions on new data that the model has never seen before. Inference can even occur locally on edge devices where physical devices meet the digital world, and routers, sensors, IoT devices close to the source of where the data is generated. This reduces network bandwidth issues and eliminates latency issues. Machine learning inference, hardware inference, running the model requires substantially less compute power than training. But inference also benefits from specialized AI chips. Machine learning, performance monitoring, and retraining, just like classic computers where software developers do regular software updates to fix bugs and increase performance and add features. Machine learning models also need to be updated regularly by adding new data to the old training pipelines and running them again. Why? Over time, machine learning models get stale. Their real-world performance generally degrades over time if they are not updated regularly with new training data that matches the changing state of the world. The models need to be monitored and retrained regularly for data or concept drift, harmful predictions, performance drops, etc. To stay up to date, the models need to learn the patterns by looking at the most recent data that better reflects reality. One last thing, verifiability, explainability. Understanding how an AI works is essential to fostering trust and confidence in AI production models. Neural networks and deep learning differ from other types of machine learning algorithms in that they have low explainability. They can generate a prediction, but it is very difficult to understand or explain how it arrived at its prediction. This explainability problem is often described as a problem for all of AI, but it's primarily a problem for neural networks and deep learning. Other types of machine learning algorithms, for example, decision trees, have very high explainability. The results of the 5-year DARPA explainable AI program, XAI, are worth reading here. So what can machine learning do? One, it's taken decades, but as of today, on its simplest implementations, machine learning applications can do some tasks better and/or faster than humans. Machine learning is most advanced and widely applied today in processing text through natural language processing into Databricks. Discover Pages, the democratization of artificial intelligence and deep learning by understanding images and videos and Anavision analytics and anomaly detection and detection. For example, recognize and understand text and natural language processing. AI is better than humans on basic reading comprehension benchmarks like SuperGLUE and SCU80, and their performance on complex linguistic tasks is almost there. Applications GP3, M6, OPT75B, Google Translate, Gmail, autocomplete, chatbots, text summarization. Write human-like answers to questions and assist in writing computer code, and AI can write original text that is indistinguishable from that created by humans. Examples, GT3, WuDao 2.0 or generate computer code. Example, GitHub Copilot, WordTune recognize and understand images and video streams, and AI can see and understand what it sees. It can identify and detect an object or a feature in an image or video. It can even identify faces. It can scan news broadcasts or read and assess text that appears in videos. It has uses in threat detection, airport security, banks, and sporting events, in medicine to interpret MRIs or to design drugs, and in retail to scan and analyze in-store imagery to intuitively determine inventory movement. Examples of ImageNet benchmarks here and here detect changes in packaged anomalies, and AI can recognize patterns which don't match the behaviors expected for a particular system. Out of millions of different inputs or transactions, these applications can discover evidence of an attack on financial networks, fraud detection in insurance filings or credit card purchases, identify fake reviews, even tag sensor data in industrial facilities that mean there's a safety issue. Examples here, here, and here. Power recommendation engines and AI can provide recommendations based on user behaviors used in e-commerce to provide accurate suggestions of products to users for future purchases based on their shopping history. Examples: Alexa and Siri recognize and understand your voice, and AI can understand spoken language. Then it can comprehend what is being said and in what context. This can enable chatbots to have a conversation with people. It can record and transcribe meetings. Some versions can even read lips to increase accuracy. Examples: Siri, Alexa, Google Assistant. Example here, create artificial images. AI can create artificial images, deepfakes, that are indistinguishable from real ones using generative adversarial networks. Useful in entertainment. Virtual worlds, gaming, fashion design, etc. Synthetic faces are now indistinguishable and more trustworthy than photos of real people. Paper here. Create artist quality illustrations from a written description. AI can generate images from text descriptions, creating anthropomorphized versions of animals and objects, combining unrelated concepts in plausible ways. An example is DALL-E generative design of physical products. Engineers can input design goals into AI-driven generative design software, along with parameters such as performance or spatial requirements, materials, manufacturing methods, and cost constraints. The software explores all the possible permutations of a solution. Quickly generating design alternatives. Example here. Sentiment analysis and AI leverages deep natural language processing, text analysis, and computational linguistics to gain insight into customer opinion, understanding of consumer sentiment, and measuring the impact of marketing strategies. Examples: Brand 2.4. Monkey Learn. What does this mean for businesses? Skip this section if you're interested in national security applications. Hang on to your seat. We're just at the beginning of the revolution. The next phase of AI, powered by ever-increasing powerful AI hardware and cloud clusters, will combine some of these basic algorithms into applications that do things no human can. It will transform business and defense in ways that will create new applications and opportunities. Human-machine teaming applications with embedded intelligence have already begun to appear thanks to massive language models. For example, Copilot is a pair programmer in Microsoft Visual Studio VS Code. It's not hard to imagine DALL-E 2 as an illustration assistant in a photo editing application, or GPT-3 as a writing assistant in Google Docs. AI in medicine A applications are already appearing in radiology, dermatology, and oncology. Examples are IDXDR OsteoDetect, Embreeze 2. AI medical image identification can automatically detect lesions and tumors with diagnostics equal to or greater than humans. For pharma, AI will power drug discovery design for finding new drug candidates. The FDA has a plan for approving AI software. Here has a list of AI-enabled medical devices here. Autonomous vehicles, harder than it first seemed, but car companies like Tesla will eventually get better than human autonomy for highway driving and eventually city streets. Decision support, advanced virtual assistants can listen to and observe behaviors, build and maintain data models, and predict and recommend actions to assist people with and automate tasks that were previously only possible for humans to accomplish. With supply chain management, AI applications are already appearing in predictive maintenance, risk management, procurement, order fulfillment, supply chain planning, and promotion management. Marketing AI applications already appearing in real-time personalization, content and media optimization, and campaign orchestration to augment, streamline and automate marketing processes and tasks constrained by human costs and capability, and uncover new customer insights and accelerate deployment at scale. making business smarter. Customer support AI applications are already appearing in virtual customer assistants with speech recognition, sentiment analysis, automated augmented quality assurance, and other technologies providing customers with 24/7 self and assisted service options across channels. AI and national security, too much like the dual use a dual nature of classical computers, AI developed for commercial applications can also be used for national security. AML and ubiquitous technical surveillance, AML, have made most cities untenable for traditional tradecraft. Machine learning can integrate travel data, customs, train line, train, car rental, hotel, license plate readers that integrate feeds from CCTV cameras for facial recognition and gait recognition, breadcrumbs from wireless devices, and then combine it with DNA sampling. The result is automated persistent surveillance. China's employment of AI as a tool of repression and surveillance of the Uyghurs is a dystopian of how totalitarian regimes will use AI, enable ubiquitous surveillance to repress and monitor its own populace. And Skywag through 2021 final report XMMLO on the battlefield, AI will enable new levels of performance and autonomy for weapon systems. Autonomously collaborating assets, e.g. drone swarms, ground vehicles that can coordinate attacks, ISR missions, and more. Fusing and making sense of sensor data and detecting threats in optical ISAR imagery, classifying aircraft based on radar returns, searching for anomalies in radio frequency signatures, etc. Machine learning is better and faster than humans in finding targets hidden in a high clutter background. Automated target detection and fires from satellite, a UAV. For example, an unmanned aerial vehicle, a UAV, or unmanned ground vehicles with onboard AI edge computers could use deep learning to detect and locate concealed chemical, biological, and explosive threats by fusing imaging sensors and chemical biological sensors. Other examples include to use AML countermeasures against adversarial, low probability of intercept, low probability of detection, LPI, LPD radar techniques in radar and communication systems. Given sequences of observations of unknown radar waveforms from arbitrary emitters without a priori knowledge. Use machine learning to develop behavioral models to enable inference of radar intent and threat level, and to enable prediction of future behaviors. For objects in space, use machine learning to predict and characterize a spacecraft's possible actions, its subsequent trajectory, and what threats it can pose from along that trajectory. Predict the outcomes of finite burn, continuous thrust, and impulsive maneuvers. AI empowers other applications such as Tear flight operations planning decision aid tool for strike operations aboard aircraft carriers, TAIN automated battle management, air and missile defense, Army, Navy tactical AML and collection. The front end of intelligence collection platforms has created a fire hose of data that have overwhelmed human analysts. Cause smart sensors coupled with inference engines that can pre-process raw intelligence and prioritize what data to transmit and store helpful in degraded or low bandwidth environments. Human-machine teaming in signals into applications with embedded intelligence have already begun to appear in commercial applications thanks to massive language models. For example, Copilot as a pair programmer in Microsoft Visual Studio VS Code. It's not hard to imagine an AI that can detect and isolate anomalies and other patterns of interest in all sorts of signal data faster and more reliably than human operators. AI-enabled natural language processing, computer vision, and audio-visual analysis can vastly reduce manual data processing. Advances in speech to text transcription and language analytics now enable reading, comprehension, question answering, and automated summarization of large quantities of text. This not only prioritizes the work of human analysts, it's a major force multiplier. AI can also be used to automate data conversion, such as translations and decryptions, accelerating the ability to derive actionable insights. Human-machine teaming in tasking and dissemination, AI-enabled systems will automate and optimize tasking and collection for platforms, sensors, and assets in near real-time in response to dynamic intelligence requirements or changes in the environment. AI will be able to automatically generate machine-readable versions of intelligence products and disseminate them at machine speed so that computer systems across the IC and the military can ingest and use them in real time without manual intervention. Human-machine teaming and exploitation and analytics, AI-enabled tools can augment filtering, flagging, and triage across multiple data sets. They can identify connections and correlations more efficiently and at a greater scale than human analysts, and can flag those findings and the most important content for human analysis. AI can fuse data from multiple sources, types of intelligence, and classification levels to produce accurate predictive analysis in a way that is not currently possible. This can improve indications and warnings for military operations and active cyber defense. AUI-ML information warfare nation-states have used AI systems to enhance disinformation campaigns and cyber attacks. This included using deepfakes, so fake videos generated by a neural network that are nearly indistinguishable from reality. They are harvesting data on Americans to build profiles of our beliefs, behavior, and biological makeup for tailored attempts to manipulate or coerce individuals. But because a large percentage of it is open source, AI is not limited to nation states. AI-powered cyber attacks, deepfakes, and AI software paired with commercially available drones can create poor, man-smart weapons for use by rogue states, terrorists, and criminals. AAML cyber warfare AI-enabled malware can learn and adapt to a system's defensive measures, or conversely, AU-enabled cyber defensive tools can proactively locate and address network anomalies and system vulnerabilities. AI-driven malware, where a malicious logic embeds machine learning methods and models to automatically probe the target system for inferring actionable intelligence, e.g., system configuration or operational patterns, and as to customize the attack, payload accordingly, e.g., determine the most opportune time to execute the payload so to maximize the impact. Attacks against AI adversarial AI as AI proliferates. Defeating adversaries will be predicated on defeating their AI and vice versa, as neural networks take over sensor processing and triage tasks. A human may only be alerted if the AI deems it suspicious. Therefore, we only need to defeat the AI to evade detection, not necessarily a human. Adversarial attacks against AI fall into three types. Data misclassification to generate false positive or negative results, test synthetic data generation to feed false information, data analysis for AI-assisted classical attack generation, AI attack surfaces, electronic attack, EA, electronic protections, EP, electronic support, ES, all have analogs in the AI algorithmic domain. In the future, we may play the same game about the algorithmic spectrum, denying our adversaries their AI capabilities while defending ours. Others can steal or poison our models or manipulate our training data. AI, friend or foe, closer to home. Because of AI, adversaries will be able to act with micro precision, but at macro scale and with greater speed. They will and to target individuals in new ways. AI will also help create precisely engineered biological agents, and adversaries will manipulate the AI systems we will rely upon. Tear first, digital dependence in all walks of life increases vulnerabilities to cyber intrusion across every segment of our society, corporations, universities, government, private organizations, and the homes of individual citizens. In parallel, new sensors have flooded the modern world. The Internet of Things in OT, cars, phones, homes, and social media platforms collect streams of data, which can then be fed in AI systems that can identify, target, and manipulate or coerce our citizens. 2. State and non-state adversaries are challenging the United States below the threshold of direct military confrontation by using cyber attacks, espionage, psychological and political warfare, and financial instruments. Adversaries do not need AI to conduct widespread cyber attacks, exfiltrate troves of sensitive data about American citizens, interfere in our elections, or bombard us with malign information on Graphic Want 1. How AI is transforming the threat landscape. Massive data sets. Machine learning algorithms tend to require large quantities of training data in order to produce high-performance AI models. Training Google's GPT-3 natural language model with 175 billion parameters takes one Hun 024 NVIDIA A100 GPUs more than 1 month. Today, strategic and tactical sensors pour in a fire hose of images, signals and other data, billions of computers, digital devices, and sensors connected to the internet, producing and storing large volumes of data, which provide other sources of intelligence. For example, facial recognition requires millions of labeled images of faces for training data. Of course, more data only helps if the data is relevant to your desired application. Training data needs to match the real-world operational data very, very closely to train a high performing AI model. Improved machine learning algorithms, the first machine learning algorithms are decades old, and some remain incredibly useful. However, researchers have discovered new algorithms that have greatly sped up the field's cutting edge. These new algorithms have made machine learning models more flexible, more robust, and more capable of solving different types of problems. Open source code, pre-trained models and frameworks developing machine learning systems required a lot of expertise and custom software development that made it out of reach for most organizations. Now, open source code libraries and developer tools allow organizations to use and build upon the work of external communities. No team or organization has to start from scratch, and many parts that used to require highly specialized expertise have been automated. Even non-experts and beginners can create useful AI tools. In some cases, open source LM models can be entirely reused and purchased. Combined with standard competitions, open source pre-trained models and frameworks have moved the field forward faster than any federal lab or contractor. It's been a feeding frenzy with the best and brightest researchers trying to one-up each other to prove which ideas are best. 3 tips UFWWU. A MIL docs understanding Toyota Center technology. PD for the downside is that, unlike past DoD technology development, where the DoD leads it, can control it, and has the most advanced technology, like stealth and electronic warfare, in most cases the DoD will not have the most advanced algorithms or models. The analogy for AI is closer to microelectronics than it is EU. The path forward for the DoD should be supporting open research, but optimizing on dataset collection, harvesting research results, and fast application. More computing power, special chips, machine learning systems require a lot of computing power. Today, possible to run machine learning algorithms on massive datasets using commodity graphics processing units and GPUs. See the machine learning hardware section below. While many of the AI performance improvement have been due to human cleverness on better models and algorithms, most of the performance gains have been the massive increase in compute performance. See the semiconductor section, more computing power, AI in the cloud, the rapid growth in the size of machine learning models has been achieved by the move to large data center clusters. The size of machine learning models are limited by time to train them. For example, in training images, the size of the model scales with the number of pixels in an image. Image and model sizes are 224x224 pixels, but HD 1920-80 images require 40x more computation memory. Large natural language processing models, e.g. summarizing articles, English to Chinese translation like Google's GPT-3 require enormous models. GP3 uses 175 billion parameters and was trained on a cluster with 124 NVIDIA A100 GPUs that cost other 25 million, which is why large clusters exist in the cloud, or the largest companies, government agencies. Facebook's deep learning and recommendation model, a DLRM, was trained on 100 TB data and has 24 billion parameters. Some cloud vendors train on 18 TB data sets. Instead of investing in massive amounts of computers needed for training, companies can use the enormous on-demand, off-premises hardware in the cloud, e.g. Amazon AWS, Microsoft Azure for both training machine learning models and deploying inferences. We're just getting started. The next 10 years will see a massive improvement on AI inference and training capabilities. This will require regular refreshes of the hardware on the chip and cloud clusters to take advantage. This is the AI version of Moore's Law on steroids. Applications that are completely infeasible today will be easy in 5 years. What can't AI do? Well, AI can do a lot of things better than humans when focused on a narrow objective. There are many things it still can't do. AI works well in specific domain where you have lots of data. Time, resources to train, domain expertise to set the right goals rewards during training, but that is not always the case. For example, AI models are only as good as the fidelity and quality of the training data. Having bad labels can wreak havoc on your training results. Protecting the integrity of the training data is critical. In addition, AI is easily fooled by out of domain data, things it hasn't seen before. This can happen by overfitting. When a model trains for too long on sample data, or when the model is too complex, it can start to learn the noise or irrelevant information within the dataset. For when the model memorizes the noise and fits too closely the training set, the model becomes overfitted, and it is unable to generalize well to new data. If a model cannot generalize well to new data, then it will not be able to perform the classification or prediction tasks it was intended for. However, if you pause too early or exclude too many important features, you may encounter the opposite problem, and instead, you may underfit your model. Underfitting occurs when the model has not trained for enough time or the input variables are significant enough to determine a meaningful relationship between the input and output variables. AI is also poor at estimating uncertainty, confidence, and explaining its decision-making. It can't choose its own goals. Executives need to define the decision that the AI will execute. Without well-defined decisions to be made, data scientists will waste time, energy, and money, except for simple cases an AI can't yet figure out cause after why something happened. It can't think creatively or apply common sense. AI is not very good at creating a strategy unless it can pull from previous examples and mimic them, but then fails with the unexpected, and it lacks generalized intelligence, e.g., that can generalize knowledge and translate learning across domains. All of these are research topics actively being worked on. Solving these will take a combination of high-performance computing, advanced AML semiconductors, creative machine learning implementations, and decision science. Some may be solved in the next decade, at least to a level where a human can't tell the difference. Where is AI in business going next? Skip this section if you're interested in national security applications, just as classic computers were applied to a broad set of business, science, and military applications. AI is doing the same. AI is exploding not only in research and infrastructure, which go wide, but also in the application of AI to vertical problems, which go deep and depend more than ever on expertise. Some of the new applications on the horizon include human-AI teaming and AI helping in programming and decision-making, smarter robotics and autonomous vehicles, AI-driven drug discovery and design, healthcare diagnostics, chip electronic design automation, and basic science research. For types of WBUM, CumCloud learn overfitting advances in language understanding are being pursued to create systems that can summarize complex inputs and engage through human-like conversation, critical component of next-generation teaming. Where is AI and national security going next? In the near future, AI may be able to predict the future actions an adversary could take and the actions a friendly force could take to counter these. The 20th century model loop of observe, orient, decide, and act, OODE, is retrospective, and observation cannot be made until after the event has occurred. An AI-enabled decision-making cycle might be sense it, predict, agree, act. AI senses the environment, predicts what the adversary might do, and offers what a future friendly force response should be. The human part of the human-machine team agrees with this assessment. An AI acts by sending machine-to-machine instructions to the small, agile, and many autonomous warfighting assets deployed in mass across the battlefield. An example of this is DARPA's ACE's Air Combat Evolution program that is developing a warfighting concept for combined arms using manned and unmanned systems. Humans will fight in close collaboration with autonomous weapon systems in complex environments with tactics informed by artificial intelligence. A once-in-a-generation event. Imagine it's the 1980s and you're in charge of an intelligence agency. SIGINT and Kuomintang were analog and RF. You had worldwide collection systems with bespoke systems in space, air, underwater, etc. And you wake up to a world that shifts from copper to fiber. Most of your people and equipment are going to be obsolete, and you need to learn how to capture those new bits. Almost every business process is needed to change. New organizations needed to be created. New skills were needed and old ones were obsoleted. That's what AAML is going to do to you and your agency. The primary obstacle to innovation in national security is not technology, it is culture. The DoD and IC must overcome a host of institutional, bureaucratic, and policy challenges to adopting and integrating these new technologies. Many parts of our culture are resistant to change, reliant on traditional tradecraft and means of collection, and averse to risk-taking, particularly acquiring and adopting new technologies and integrating outside information sources. The history tells us that late adopters fall by the wayside as more agile and opportunistic governments master new technologies. Carpe diem, and want more detail? Read on if you want to know about machine learning chips, see a sample machine learning pipeline and learning about the 4 types of machine learning. Artificial intelligence machine learning semiconductors skip this section if all you need to know is that special chips are used for AIML, AML semiconductors, and high performance computing are intimately intertwined and progress in each is dependent on the others. See the semiconductor ecosystem report. Some machine learning models can have trillions of parameters and require a massive number of specialized AI chips to run. Edge computers are significantly less powerful than the massive compute power that's located at data centers and the cloud. They need low power and specialized silicon. Why dedicated AI chips and chip speed matter? Dedicated chips for neutral nets, e.g. NVIDIA GPUs, Xilinx FPUs, Google TPUs are faster than conventional CPUs for 3 reasons. 1, they use parallelization. 2, they have larger memory bandwidth. And 3, they have fast memory access. There are 3 types of AI chips. To graphics processing units, GPUs use thousands of cores. Parallel workloads, widespread use in machine learning field, programmable gate arrays, FPGAs good for algorithms, compression, video encoding, cryptocurrency, genomics, search. Need specialists to program paint applications. Specific integrated circuits, ASICs, custom chips, e.g. Google TPUs, matrix multiplication plays a big part in neural network computations, especially if there are many layers and nodes. Graphics processing units is GPUs contain hundreds or 1,000s of cores that can do these multiplications simultaneously. And neural networks are inherently parallel, which means that it's easy to run a program across the cores and clusters of these processors. That makes AI chips tens or even 1,000 of times faster and more efficient than classic CPUs for training and inference of AI algorithms. State-of-the-art AI chips are dramatically more cost-effective than state-of-the-art CPUs as a result of their greater efficiency for AI algorithms. Cutting-edge AI systems require not only AI-specific chips, but state-of-the-art AI chips. Older AI chips incur huge energy consumption costs that quickly balloon to unaffordable levels. Using older AI chips today means overall costs and slowdowns at least an order of magnitude greater than for state-of-the-art AI chips. Cost and speed make it virtually impossible to develop and deploy cutting-edge AI algorithms without state-of-the-art AI chips. Even with state-of-the-art AI chips, training a large AI algorithm can cost tens of millions of dollars and take weeks to complete. With general-purpose chips like CPUs or older AI chips, this training would take much longer and cost orders of magnitude more, making staying at the R&D frontier impossible. Similarly, performing inference using less advanced or less specialized chips could involve similar cost overruns and take orders of magnitude longer. In addition to off-the-shelf AI chips from NVIDIA, Xilinx and Intel, large companies like Facebook, Google, Amazon have designed their own chips to accelerate AI. The opportunity is so large that there are hundreds of AI accelerator startups designing their own chips, funded by tens of billions of venture capital and private equity. None of these companies own a chip manufacturing plant, a fab, so they all use a foundry as an independent company that makes chips for others, like TSMC in Taiwan, ZRSM in China for defense-related silicon. A sample of AI GPU, FPGA and ASIC chips, and where they're made, IPs, intellectual property vendors also offer AI accelerators. AI chip designers can buy AI IP cores, pre-built AI accelerators from Synopsys, EV, SumC's, XK, Cadence, Tensilica, AI, ARM, Ethos, Siva, Sensper2, Nupro Imagination Series 4, ThinkSilicon, Neox, LexLogic 8, FPGA, Edge, Cortex, and others. Other AI hardware architectures, spiking neural networks. SEN is a completely different approach from deep neural nets. A form of neuromorphic computing, it tries to emulate how a brain works. SNN neurons use simple counters and adder. No matrix multiply hardware is needed and power consumption is much lower. SNNs are good at unsupervised learning, e.g. detecting patterns in unlabeled data streams. Combined with their low power, they're a good fit for sensors at the edge. Examples: BrainChip, Gray Matter, Innatera, Intel. Analog machine learning AI chips use analog circuits to do the matrix multiplication in memory. The result is extremely low power AI for always-on sensors. Examples: Mythic AMP, Aspinity's AM100 Tetramem. Optical photonics AI computation promise performance gains over standard digital silicon, and some are nearing production. They use intersecting coherent light beams rather than switching transistors to perform matrix multiplies. Computation happens in picoseconds and requires only power for the laser. Though off-chip digital transitions still limit power savings. Examples: light matter, lightelligence, Luminous, light and AI hardware for the edge as more AI moves to the edge. The edge AI accelerator market is segmenting into high-end chips for camera-based systems and low-power chips for simple sensors. For example, AI chips in autonomous vehicles, augmented reality and multi-camera surveillance systems. These inference engines require high performance. Examples: NVIDIA Orin, AMD Versal, Qualcomm Cloud AI 100, and Acquire Driver for automotive software. AI chips and cameras for facial recognition surveillance. These inference chips require a balance of processing power with low power. Putting an AI chip in each camera reduces latency and bandwidth. Example is Halo 8, Ambarella CV5S, Quadra Q16. A Realtek 3960N ultra-low power AI chips target IT sensors. IT devices require very simple neural networks and can run for years on a single battery. Example applications: presence detection, wake word detection, gunshot detection. Examples: Synchant and NDP Inatura brain chip. AML hardware benchmarks. While there are lots of claims about how much faster each of these chips are for AMML, there are now a set of standard benchmarks, ML Commons. These benchmarks were created by Google, Baidu, Stanford, Harvard, and UC Berkeley. One last thing, non-NVIDIA AI chips and the NVIDIA software moat. New AI accelerator chips most deal with the software moat that NVIDIA has built around their GPUs. As popular AI applications and frameworks are built on NVIDIA Qt software platform, if new AI accelerator vendors want to port these applications to their chips, they have to build their own drivers, compiler, and other tools. Details of a machine learning pipeline. This is a sample of the workflow a pipeline data scientists use to develop, deploy, and maintain a machine learning model. Let's see the detailed description here. The types of machine learning-fied. Skip this section if you want to believe it's magic. Machine learning algorithms fall into 4 classes: supervised learning 2, unsupervised learning 3, SEMI, supervised learning 4, reinforcement learning. They differ based on what types of data their algorithms can work with here for supervised and unsupervised learning. Whether or not the training data is labeled or unlabeled, TNA supervisor. A human or a software system accurately labels each of the training data inputs with its correct associated output. Note that pre-labeled data is only requiring uses to train the operation, and they'll be generating the A will be AI algorithms, the inferenderens, the for Ejaija's own labels. The accuracy of which will depend on the AI's training. Supervised learning can achieve extremely high performance, but they require very large labeled datasets to using labeled inputs and outputs. The model can measure its accuracy and learn over time. For images, a rule of thumb is that the algorithm needs at least 5,000 labeled examples of each category in order to produce an AI model with decent performance. In supervised learning, the algorithm learns from the training dataset by iteratively making predictions on the data and adjusting for the correct answer. Farewell. Supervised learning models tend to be more accurate than unsupervised learning models. They require upfront human intervention to label the data appropriately. Supervised machine learning category examples: classification problems use an algorithm to assign data into specific categories, such as separating apples from oranges, or classify spam in a separate folder from your inbox. Linear classifiers support vector machines. Decision trees and random forest are all common types of classification algorithms. P-regression understands the relationship between dependent and independent variables, helpful for predicting numerical values based on different data points, such as sales revenue projections for a given business. Some popular regression algorithms are linear regression, logistic regression, and polynomial regression. Example algorithms include logistic regression and the backpropagation neural network, unsupervised learning. These algorithms can analyze and cluster unlabeled data sets. They discover hidden patterns in data without the need for human intervention, hence they're unsupervised. They can extract features from the data without a label for the results tier. For an image classifier, an unsupervised algorithm would not identify the image as a cat or a dog. Instead, it would sort the training data set into various groups based on their similarity. and unsupervised learning systems are often less predictable. But as unlabeled data is usually more available than labeled data, they are important, and unsupervised algorithms are useful when developers want to understand their own datasets and see what properties might be useful in either developing automation or change operational practices and policies. They still require eventually some human editing the output. Gregory C. for Gregory C. Allen Dodd-Joint AI Center different ways. A basic understanding of these strengths, weaknesses, and failure modes can help you understand whether or not your particular problems are a good fit for a learning AI solution. BIDRE, TF, ARN, TAT, TYPS, OF, MyCIER, and NG. How you do a THEDFR, like artificial intelligence, machine learning is also an umbrella term, and there are 4 different broad families of machine learning algorithms. There are also many different subcategories and combinations under these 4 major families, but a good understanding of these 4 broad families will be sufficient for the vast majority of DoD employees, including senior leaders in non-technical roles. Important distinction is whether or not the training data is labeled or unlabeled and how the system receives its data inputs. Figure 3 provides a simple illustration of labeled and unlabeled training data for a classifier of images of cats and dogs. Depending upon whether or not data is labeled, a different family of algorithms applies. The 4 major families of algorithms are supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Supervised learning, supervised means that before the algorithm processes the training data, some supervisors, which may be a human, group of humans, or a different software system, has accurately labeled each of the data inputs. Unsupervised machine learning categories and examples take clustering groups, unlabeled data based on their similarities or differences. For example, K-means clustering algorithms assign similar data points into groups, where the K-value represents the size of the grouping and granularity. This technique is helpful for market segmentation, image compression, etc. Association finds relationships between variables in a given data set. These methods are frequently used for market basket analysis and recommendation engines along the lines of customers who bought this item also bought recommendations. Dimensionality reduction is used when the number of features or dimensions in a given data set is too high. It reduces the number of data inputs to a manageable size while also preserving the data integrity. Often, this technique is used in the preprocessing data stage, such as when autoencoders remove noise from visual data to improve picture quality. Example algorithms include a priori algorithm, and K means difference between supervised and unsupervised learning. The main difference labeled data 8 goals. In supervised learning, the goal is to predict outcomes for new data. You know upfront the type of results to expect. With an unsupervised learning algorithm, the goal is to get insights from large volumes of new data. The machine learning itself determines what is different or interesting from the data set. Applications, supervised learning models are ideal for spam detection, sentiment analysis, weather forecasting, and pricing predictions, among other things. In contrast, unsupervised learning is a great fit for anomaly detection, recommendation engines, customer personas, and medical imaging. Complexity supervised learning is a simple method for machine learning, typically calculated through the use of programs like R or Python. In unsupervised learning, you need powerful tools for working with large amounts of unclassified data. Unsupervised learning models are computationally complex because they need a large training set to produce intended outcomes. Drawbacks: supervised learning models can be time-consuming to train, and the labels for input and output variables require expertise. Meanwhile, unsupervised learning methods can have wildly inaccurate results unless you have human intervention to validate the output variables. Semi-supervised learning, semi-supervised algorithms combine techniques from supervised and unsupervised algorithms for applications with a small set of labeled data and a large set of unlabeled data. In practice, using them leads to exactly what you would expect: a mix of some of both of the strengths and weaknesses of supervised and unsupervised approaches, and Understanding Artificial Intelligence Technology, Gregory C. Allen Dodd-Joint AI Center. It is not true that unsupervised learning is worse than supervised learning, as though performance can be lower for some use cases. Rather, unsupervised learning is useful for solving different types of problems. A common unsupervised use case is fraud detection in financial data. In the case of fraud detection, supervised learning could be a good fit for identifying potential fraud that matches behaviors known to be unlawful or associated with fraud. Unsupervised learning can find new, unidentified patterns of behavior that might indicate new types of fraud techniques. The typical algorithms are extensions to other flexible methods that make assumptions about how to model the unlabeled data. An example is generative adversarial net photographs can generate new photographs that look authentic to human observers. Deepfakes, reinforcement learning paying training data is collected by an autonomous, self-directed AI agent as it perceives its environment and performs goal-directed actions. Then the rewards are input data received by the AI agent when certain criteria are satisfied. Then these criteria are typically unknown to the agent at the start of training. Then rewards often contain only partial information. They don't signal which inputs were good or not tanned. The system is learning to take actions to maximize its receipt of cumulative rewards. The reinforcement AI can defeat humans in chess. Gohan, there are no labeled data sets for every possible move. There is no assessment of whether it was a good or bad move. Instead, was partial labels reveal the final outcome, win or lose. The algorithms explore the space of possible actions to learn the optimal set of rules for determining the best action that maximize wins. Reinforcement machine learning categories and examples, pair algorithm examples include DQNS, a deep Q network. DPG is deep deterministic policy gradient. A3C is asynchronous advantage actor. Critic algorithm, AFSIQ, learning with normalized advantage functions. Zaytern AlphaGo, a reinforcement system played 4.9 million games of Go in 3 days against itself to learn how to play the game at a world champion level. Their reinforcement is challenging to use in the real world, as the real world is not as heavily bounded as video games and time cannot be sped up in the real world. There are consequences to failure in the real world. Sources: Ping Understanding AI Technology. Greg Allen, Chief of Strategy and Communications, Joint Artificial Intelligence Center, JIC, Department of Defense, EPS2WIOA, Mill Docs Understandings and 20% Technology, PIF Understanding Artificial Intelligence Technology, Gregory C., Allen Dawdy Joint AI Center, Semi-Supervised Learning. There is also an increasingly popular class of semi-supervised algorithms that combine techniques from supervised and unsupervised algorithms for applications with a small set of labeled data and a large set unlabeled data. In practice, using them leads to exactly what you would expect, a mix of some of both of the strengths and weaknesses of supervised and unsupervised approaches. Reinforcement learning. In reinforcement learning, the training data is collected by an autonomous, self-directed AI agent in the course of perceiving its environment, which might be the real world or a simulated environment, and performing goal-directed actions, is trying to maximize receipt of rewards. 4 aspects of reinforcement learning are notably distinct from supervised and unsupervised learning. 1, data is gathered by the AI agent itself in the course of its interacting with the environment and perceiving stated changes. For example, an AI agent playing a digital game of chess makes moves and perceives changes in the board based on its moves. 2, the rewards are input data received by the agent when certain criteria are satisfied. For example, a reinforcement learning AI agent in chess will make many moves before each win or loss. These criteria are typically unknown to the agent at the outset of training. 3, rewards often contain only partial information. A reward, like a win in chess, conveys that some inputs must have been good, but it doesn't clearly signal which inputs were good and which were not. 4, the system is learning an action policy for taking actions to maximize its receipt of cumulative rewards.